you see the slides? Perfect. Thanks.
And maybe another person yet, or
yeah, I can also try.
Try that? Yeah.
Yes. Fine.
Yeah, it's fine.
Okay, thank you.
So I think it's about time to start. We started at the top of the hour, right? So shall we start?
Sorry, yes, well, normally it was at 5, but yeah, we are all set, I guess. So maybe we can start as you all want.
Perfect, thank you.
Great.
Right, well, thank you very much for joining us today for a session dedicated to buildings and energy use in buildings, of course. So we have lined up 3 very interesting presentations. The fact that we have 3 presentations instead of 4 means that the speakers can take a little more time to do their presentation. Maybe instead of the traditional 20 minutes, we can have the luxury of having maybe 22 and have about 8 minutes for questions. Questions from the audience at the end of the presentation. You guys can unmute yourselves. You guys can use the hand. You will get technical assistance from us. And the speakers will set their own rules in terms of asking clarification questions in the middle of the presentation. So having said that, I'm really looking forward to the first presentation, which is going to be by Amir, Ashour, Novirdoust. How did I pronounce that?
Very nice, thanks.
Very good. Okay, so the floor to you. Please share your screen with us and take it away.
Do you see the presentation? Perfect. So thanks for attending this session. My name is Amir Ashour Novirdoust. I work at the Institute of Energy Economics at the University of Cologne as a researcher here. And I'm going to present our collaborative research project with the name of Modeling Optimal Regional Energy Supply based on 3D geodata for buildings and renewable energies. It's a collaborative work with EWI, our institute, and Hochschule für Technik at Stuttgart, University of Stuttgart. As a brief overview of the talk today, first I'm going to start with the motivation, continue with some overview of the literature that has been done that is relevant for our work, and then talk about our methodology. And then for the 4th step, we have the scientific contribution of the results. And to be clear here, these are expected results as we have not confirmed results yet. We are in the conceptual phase of this research, and then also give an outlook about the next steps and what has to be done in the further steps. Ah, yeah, and I forgot to mention questions you can ask at the end of the presentation, or if you like clarification questions, you can interrupt at any time, just unmute yourself. Might be helpful to raise questions right away. So the motivation, I think it's nothing new that everybody knows. The energy transformation aims at replacing CO2 intensive fossil fuels by renewable energy sources. And this has many major implications, a few of which I want to focus here are that renewable energy sources are typically much less energy dense, which means that there is more area requirements for that, as well as, and this comes with implications on transportation. For example, just consider biofuels, that you have higher efficiency when you have spatial proximity of production and consumption of energy sources. And these points stress the increasing importance of unique geographic characteristics of energy systems, due to the decentralization. Like points like availability of renewable primary energy sources, such as wind, radiation, or biomass. And this includes potential areas for the renewable energy sources, as well as the potential regarding weather conditions and soil conditions, as well as the umbrella term of economic activity, where we have population density, also the building stock and the refurbishment level of the building stock, energy demand, things like this. These points increasingly matter, and on the other side, they are highly regionally heterogeneous, so heterogeneous across the regions, and the spatial distribution of these factors is not is highly uneven, and therefore understanding the impact of these characteristics of the regions and how the characteristics interplay with national energy policy is of increasing importance for policymakers, as it might lead to a more efficient energy transition to understand the uptake of energy policies based on regional characteristics. So a very brief overview about the literature that has been done that is relevant for our methodology, for our approach. There we identify 3 branches. We have the geographic land use modeling, the regional energy system modeling, and spatial energy policies. And of course, the papers that are depicted here and put into one of these buckets, there's some overlaying, but this, yeah. The first one, the geographic land use modeling, is often used to assess potentials for renewable energy deployment and where you can efficiently put renewable energies. These are often based on energy balances rather than cost-based optimization, but they're very suitable to identify suitable areas for different kinds of renewable energy sources. And this literature brand includes theoretical considerations regarding land use change and also the role of strategic planning. On the other hand, on the right side, we have regional system modeling. So here we have, for example, papers that do a regional impact of a set of energy transition scenarios on land use, employment, emissions, and also system costs. We have bottom-up optimization of the building sector on a national level. And then as the last branch that we identified here, we have the spatial energy policies. And in general, these are a combination of social sciences, energy research, also rural studies to understand peculiarities of the energy transition in different regions. For example, already in 2003, Hein and other researchers identified in England a high potential of rural areas to contribute to the energy transition. But coming with that, there's a high need for better tailored policies and regulation instead of one-size-fits-all policies. And lastly, we understand our work in the intersection, or let's say in the middle of these branches, as we want to model a regional energy system based on geoinformation data, where we aim at modeling both the building stock, the building sector, within the energy based on realistic representation of potentials for renewable energies, as well as demand from the building sector. So coming to the methodology, I hope this slide is not overwhelming. It is quite a lot of steps here in the methodology, and this is not our research project now, but the methodology of a former research project. So based on my colleagues, Theile and other, and also me and the colleagues from HFT Stuttgart that I mentioned. So this is forthcoming work. Here, this model aimed at modeling a consumer-based investment decision based on realistic representation of the building. So I'm going to start with the 2 models that are coupled here, SimStat is a 3D building model. It calculates energy demand based on 3D data that is available for a building. So here on the left side, we see what enters the model. It is the building geometry, the building usage, and the year of construction. Also, you need some databases for weather profiles and some other libraries. And the output of Zimstadt is hourly energy profiles for, let's say, PV potential and energy potentials. And these hourly values then enter Komodo together with some economic conditions for energy and technology prices and the regulatory framework. And Komodo is a cost-based consumer optimization model. It outputs the optimal technology diffusion of a household. So as an output, we have the technology operation profiles, the energy investment decisions for heating, solar investment, also storage investments, and lastly, also the total costs. So this is the model chain that our approach is based on. And now for this work that I'm presenting, we expanded the approach to the regional level, which gives us this here, the same data enter Zimstadt. But first, we don't, Zimstadt does not produce hourly energy profiles, but for hourly energy profiles for a set of buildings, but yearly energy profiles for the whole region. And these yearly profiles are used for the whole region, for buildings, is used in the clustering to get a set of representative buildings to represent the building stock of a region. Then these results are fed back to Zimstadt, and Zimstadt produces hourly energy profiles for this set of representative buildings. So we get the same results, such as PV potential and energy demand for this set of representative buildings, as well as area potentials for the renewable energy sources, also based on real 3D on GIS data, on geodata. So here, these energy profiles for the representative buildings and the area restrictions enter the regional energy model, again with the economic conditions, to get, again as an output, based on a cost-based optimization model, the optimal technology diffusion with accounting for the feedback of the building sector, and we get regional renewable energy sources, investments, and also the costs. Yeah. Then diving more into the concrete modeling of this approach, we have in our model, we have two branches that need to come together. So we have the modeling of the supply on the one side and the modeling of the demand, the endogenous demand on the other side. So the building sector is modeled endogenously, as I said. So on the right-hand side, there is no big surprises. It's a cost-based optimization. So we have the total cost of the building sector is the costs of the investment costs, the fixed operation and maintenance costs, revenues and remuneration, and energy-based costs. Please have in mind that this is a highly simplified version of our model and the equations. On the left-hand side, we have the modeling for the investment in renewable energy sources and the land use conflict. So this free area would be a parameter that comes from the Zimstadt workflows. It gives us the area that is free within a region to use for renewable energy sources. And here we have the oversimplification that all the areas are suitable for all renewable energy technologies or crops, which of course is a simplification, but just to make this point, you might model it as a one-to-one relationship. So the area that is used for open space PV systems cannot be used for cultivating biomass, and the area that is used for installing wind power plants cannot be used for open space PV systems, and so on and so forth. And then wind, again, has this special limitation because the area that is used for wind is interpreted as the footprint of the wind power plant. And of course, you can't install a footprint next to footprint next to footprint, but you need space between it. So the capacity of wind power plants that can be installed within a region is also limited by some upper cap, which the workflows can give us. So this is a simplified version of how you could model this kind of relationship. Other considerations here are that you can have agro PV, where biomass and open space PV systems can be installed on the same area with some minor lower efficiency. So this is still in discussion whether to implement it or not, but the model could do either way. So lastly, the region minimizes the total costs that the region faces, which is subject to operation constraints, of course, and energy balances. And the total costs consist of the investment costs of the renewable energy sources, again, the operation and maintenance costs, the revenues and remuneration, the total costs of the building sector, and then also costs for supply from the grid or remuneration for energy supply to the grid, to the national grid. And this is also a point that I will come to in a few seconds. So I have depicted here some relevant metrics that we identify as important parameters for our model and for the results. Most interestingly, of course, on the upper right side, the yellow boxes, we have the regional characteristics, weather profiles, and the overall free spaces, but also very importantly, the energy potentials per area for different different technologies in the region. So just consider the soil, the constitution of the soil, that determines the potential yield of different crops and therefore the efficiency of this biomass cultivation in this area. So these differ, and the workflows for biomass will give us actual realistic representation of the efficiency of biomass, the differing efficiency of biomass in the different regions. The load, of course, depends on the building sector investments and is endogenous here, and therefore also has an interplay with the regional characteristics. Of course, some exogenous factors. We will enter the load based on exogenous factors representing all the sectors but the building sector. And then we want to use the grid capacity as a parameter that you can tune to actually model some scenarios such as self-sufficiency or more or less self-sufficiency, and analyze how the regions react to this kind of limitation and draw conclusions to the regional characteristics, such as how does a rural region react to this limitation, or how does a more urban region react to that. Prices, of course, we need for that. If the region is not self-sufficient, we need to have some energy prices from the over a supra-regional level, and there you can also imagine having time series for prices for different kind of scenarios. Going to the next slide. Yeah, so what is the scientific contribution of our results? Here I have two areas of points that I want to talk about. One is determining spatially resolved energy transition paths. So we expect to see the optimal technology diffusion for the regions with consideration of spatial peculiarities regarding one, the building sector, how much it is retrofitted, what kind of buildings are there, what is their energy demand based on actual 3D model data, based on grid capacities, as I just talked about, and also very importantly, based on regional potentials for renewable energy sources And again, this includes both free spaces as well as weather and soil conditions.
Sorry, 5 minutes left.
Oh yeah, thank you. I think I'm also close to the end. Yeah, and this also includes the final energy conversion in the building sector. So this here analyzed with consideration of the interaction with the regionally optimal energy supply. So we have the optimal technology diffusion of the region and the optimal technology diffusion of the building sector with consideration of the interaction between them. So which kind of biomass is optimal, which kind of renewable energy sources are optimal. And lastly, this will give us spatially resolved abatement cost curves. And as we have not seen this a lot in the literature, this will be quite helpful and brings me also to the next point for policymakers, as they can evaluate spatially heterogeneous responses to national policies, as regions do not have the same abatement cost curves. Also, they don't have the same characteristics and react heterogeneously on national policies. Lastly, we think that this model can justify and be a guidance for spatially resolved policies targeted at the energy transition. If you consider subsidies or taxes for certain technologies in the building sector, this model might be a guidance on how to construct or design subsidies, which are not one size fits all. And the outlook, of course, is that we need to model our 4 regions in Germany, which is Dithmarschen, Ilm-Kreis, Ludwigsburg, and Köln, that we have data on and started to model. We have this is a set of rural areas, urban areas, and also in between suburban areas. Lastly, we need to determine the renewable energy potentials with the GIS-based workflows. And then, as I said, this modeling of the land use conflict was a very simplified version. So this needs to be specified. I'm very hoping to discuss on that maybe a little bit. And lastly, assess results, draw conclusions about the connection of the regional peculiarities and the energy outcome model outcomes. So if we see differing outcomes, draw conclusions on what that is and what it's based on, and then potentially draw policy implications for that. So this is the literature that I talked about in the beginning. And this is the end of my talk. Thank you.
Well, thank you very much. That was extremely interesting. I would now like to open the floor for questions from the audience or the other participants, the other presenters as well. So any questions for Amir?
Yeah, I have a few questions, just like general curiosity, I guess. So as far as I understood, it's the work in progress. The model, does the model exists, or and you'll be using it for a certain case study, or are you going to develop a certain part of it? Like, which part are you going to focus on? Or in general?
Yeah, sorry, I think I closed the presentation, but it's fine. Yeah, so the model broadly exists. Like I said, the coupling of Simstadt and Komodo existed, and we wrote the paper on that. It's forthcoming, and we already started expanding it to the national level, regional level, and this extension already exists, and the workflows for the renewable energy potentials also mostly exist. So biomass exists, I guess, PV exists, and wind is in the working. So these things exist, and the final model coupling and bringing everything together is in the making.
So you're kind of expanding from like a small level, from the city level to regional level, right?
No, Komodo was on the building level, actually. It was a single building level. And now we're expanding that to the building sector together with regional energy balances and exogenous demand, and therefore constructing this regional level.
It's very curious because I also worked at the HFT and I heard a lot about Simstadt, but I never really get into it because I didn't work on it. So nice to see that it's like the work is picking up further.
Yes.
Another question would be like, I'm just really curious about agro PVs like that you mentioned, because I also did similar kind of work before, GIS-based analysis, and are they already like, are there many more projects on with agro PV? Is it coming up? Because you are taking the assumption that this technology exists and you are assessing the potential.
You're exactly right. And I do not know if there is a lot of actual projects taking this on. And therefore, I would not right now model it as a possibility to use agro PV. Because I wouldn't need to know more about if it is actually how you say if there is already a lot of implementation, if it's already
because it's an established technology to assume that it will.
Yeah, so that's what I meant. One could consider this and look into it if it's already a technology that is reasonable to consider in the model or not.
Okay, thank you very much. Yeah,
Thank you.
Good luck with your work.
Thanks.
Very curious.
Great. Any other questions for Amir? So maybe I'll ask a question of my own, if that's okay, Amir. I am not an expert in the kind of models that you are using. And in fact, it sounds like, there are models that are in existence and you're linking them together in different ways. But I do have a question about, your definition of regions. So you've been talking about, this is a main contribution of your paper, and I wasn't clear what your region is, whether your region is a Bundesland or if your region is an arbitrary region that is created by the model itself by constructing something that is homogeneous with respect to, to the cost of setting up PVs or the availability of land and that kind of stuff. So would you mind explaining that a little bit?
Yeah, that is an excellent question because for some of the regions that I mentioned Dithmarschen, Ludwigsburg, Ilmkreis, and Cologne. So these are cities. This is just a city. So it's not the Bundesland. But of course, the model is also flexible enough to do, how you say, municipalities, which are a subset of the city or quarters. Yeah, so right now we're considering cities with different sizes, so rural cities, and then it's really just a rural city, so not you have some kind of Kreise, which is the connection of a few cities, but right now we're considering only single cities, but it is open. This model is open for flexible to also consider quarters. I think, yeah.
Great, thank you. Any other questions for Amir? Well, if you, surely you will come up with questions the moment that we finish the session. So if you do, feel free to email Amir or to send a message, through the chat feature and everything. Amir, I would like to thank you again for your presentation and your handling of the questions. And maybe if that's okay, we can move on with the next presenter. And the next presenter is Ardak Akhatova. Is that, how did I pronounce that?
It's good. It's
acceptable.
Ardak Akhatova, yeah, acceptable. It's
right, so,
almost the same.
Thanks again, Amir.
Okay, let me share my screen. So, do you hear me well? Perfect. Oops. So my name is Ardak Akhatova. I'm from Energy Economics Group at TU Wien in Vienna. and I'm really honored to be able to present conceptualization, the ongoing work on the conceptualization of an agent-based model of neighborhood-level building retrofits based on Energiesprong approach. So I worked together with a fellow PhD student from TU Delft, Javanshir Fouladvand, as well as my supervisor, Lukas Kranzl. And the presentation will consist of the following parts. So first I will provide the motivation behind this work and some little background information on what is Energiesprong and what's agent-based modeling. I guess you're already wondering. And we'll also state my research aim, what I'm trying to tackle with this model. And then I will delve into the conceptualization phase. So the basic building blocks, and this is the, yeah, as I said, ongoing work, and there are lots of open questions, and I will finish off with some future work to be done. So let's begin. We are all well aware that despite lots of policy incentives, the rate of energy efficient renovation, retrofitting, with the abbreviation ER later, it's still very low, especially when it comes to deep energy, deep retrofitting. It's only around 0.2%, which is extremely low. So it still indicates that there are lots of barriers to energy efficient renovation, and they are at different points in the value chain, starting from the initial decision to energy efficient renovation, through financing, up until the completion of the projects. And if we focus on this initial decision to renovate, to do an energy efficient renovation, there are lots of factors that affect building owners' decisions. They can be like grouped into financial, personal, contextual factors. Of course, there's lots of social scientific literature on that. However, I could see that they only focus on one group, mostly owner-occupiers, although there are the decisions to retrofit depend largely on what is the ownership structure in the building. Also, these decision-making, they are not formalized and can hardly be used in the models, like quantitative renovation models. Also, if we look into the previous models of energy efficient renovations, as I said, they are largely focused on owner occupiers. It's understandable because they are 70% of all the owners in Europe. However, we also have private rented, social rented households, which should not be omitted, of course. And the decisions in those models are macro scale decisions, or we assume homogeneous actors and aggregate agents. Also, they mostly focus on the conventional way of retrofitting, so this classic contractor-supplier structure. However, there are some novelties in the renovation area, especially in deep renovation. This is the Energiesprong approach. It relies on the standardized facade and roof systems. So they are designed and prefabricated in their factories by a consortium of retrofitting innovators, and they are offered as a package or bundle of integrated solution. And they promise net zero performance, so net zero energy buildings. And they are also installed like within a week, and the occupants can stay inside the house. Also, if the demand is high, so if you can collect lots of homogeneous building stock, it's assumed that to have lower costs due to this economies of scale, right? And yeah, and the last point of it, the novelty is that the business model is quite peculiar. We have a new actor, which is an intermediary agent who coordinates the process. And of course, the retrofitting solution provider is like a consortium of different companies who build those facades together. But also, if we look at this modeling part of retrofitting, Nowadays, agent-based modeling is, maybe you've heard about it, it's becoming more and more applied in policy making. It's a simulation type model. It can give, like, by being able to focus on the decision making of each agent, for example, a building owner, we can make them interact with different agents. We can also create heterogeneous agents and certain rules how they interact. And then we can see, while simulating, while introducing policy incentives or different conditions in scenarios, we can see an emergent insight from this behavior. And there are very few agent-based models of retrofitting decisions. I've identified like 3 solid models, which are also highly exploratory and have different approaches. But yeah, there's still a lot to do in this area, especially when it comes to decision making of building owners. So the aim of my agent-based model, for now it's just a conceptual, is to explore policy intervention for stimulating the adoption of retrofitting, of these retrofitting packages I mentioned before, by building owners. And the focus will be on the decision on how these building owners make decisions, what affects them, and their interactions with the intermediary, this new intermediary actor. The model will be in a neighborhood level. There are many reasons for that. Firstly, because there are lots of co-benefits in focusing on the neighborhood and district level. For example, positive energy districts, energy communities, they are right now kind of picking up. And also it's in the neighborhoods, you always find buildings with different ownership types, and you can play with it a bit. Also, this smaller scale is quite suitable for agent-based models. So I cannot, it's really hard to do regional models, as for example, Amir has showed us. It would be really hard. So my main research question is, so what policy interventions and socio-techno-economic conditions will enable the integrated net zero retrofitting of existing neighborhoods? So what I mean by socio-techno-economic conditions, so for example, for techno-economic conditions, we can vary the costs of retrofitting packages, explore different solutions and their prices. Also, we can play with energy prices and CO2 prices. In the socio-economic conditions, it could be like we can see different income, age, education, such characteristics. Also play with the awareness, information level, social connectedness of the neighborhood. And of course, in policy interventions, for example, one big policy intervention would be to introduce such intermediary agency for active promotion of renovation. And this will be my, for now, main narrative, main scenario for now. And let me explain the general model framework. This is completely from scratch, although I rely on the previous literature I mentioned. So there's going to be a techno-economic evaluation submodel, which will determine the retrofitting options for the building archetypes in the neighborhood. I will talk later about how techno-economic evaluation will approximately work. And then after the retrofitting options are identified and their costs are identified, agents will choose a suitable retrofitting package for himself based on his decision-making framework, or not choose anything. Of course, that's also a possibility. And then it will be possible to simulate several scenarios. So let me explain the techno-economic evaluation submodel. This is just, as I said, for now, an idea. Once the neighborhood is selected, let's say a municipality has a plan to renovate this neighborhood, or it's just a really neighborhood with old buildings. And after it's selected, the buildings are analyzed and they are archetyped according to the Tabula project. So they have for different countries several archetypes according to years, and we can identify their approximate energy efficiency rate. And then after the building stock is analyzed, we can try to provide the retrofitting solutions. So they will be like on 3 levels. First, I mean, there are lots of measures, right? And we just try to like cluster them into 3 different types. One would be the building envelope insulation. And the second would be the heating system improvement. The third type would be the installation of renewable energy technology. And yeah, this part is still like has to be done in cooperation with my colleague. We will work with Energy Plus building simulation, and we can test out some possible solutions. And in the last step, the cost will be estimated, so we can estimate the cost of retrofitting package when it's done, for example, only in a building level, or when it's done in a neighborhood scale, to see if there are some cost benefits. And then let's say the output will be several options with costs and savings. And this information will flow into the agent's decision making. So agents will choose to adopt a certain retrofitting based on their decision making framework, as I said, or rules. This type of agent-based model derives in the theories of diffusion of innovation. And it's mainly like well used for policy guiding agent-based models. And the decision-making agents in my model are owner-occupiers. Like for now, I decided to just for the first version of the model, I will probably focus on owner-occupiers because they are a little bit more research. There's a little bit more information on how they decide. And if it works out, it would be great to also test out how private landlords would make decisions and explore that area as well. But probably they will be just introduced like one by one, not just a mix of them in the same simulation. And then another important agent is the intermediary agent. As I mentioned, it's a proxy for this market development team in Energiesprong, or also maybe you've heard about one-stop shops. They usually inform the homeowners about retrofitting options, and it's like a one place where homeowners can get information. And of course, they should be also related with buildings. So we have buildings assigned to, let's say, owner-occupier. So we have single family. In the model, I'll differentiate between single family house and multifamily building. So single family building only has one owner, one entity. It's either owner-occupier, private landlord, or social housing association. And multifamily house can have one owner or a number of owners. And yeah, so and the next step, so what do I mean by decision-making framework of agents? So building owner agents will decide whether to adopt a certain retrofitting package or not. And for now, like there are lots of decision-making. It can be as complex as it can derive from social scientific work. And, but for now, I decided for the first model to focus on more like economic decision-making, and I will derive from the work of Liang et al. He uses the utility theory and cost-benefit analysis. So assume that the agent will decide based to maximize its utility, overall satisfaction from the energy efficient retrofitting. So utility in this case means economic benefit, and economic benefit is perceived profit from the energy efficient retrofitting, which is the revenues minus costs. And revenues are savings that are from energy bills, which depend on the current costs of energy, and the government subsidy if it exists. And of course, we can later include non-monetary benefits. We'll have to find a way to monetize them. And then savings in energy bills, of course, energy demand after minus energy demand before, multiplied by area and energy price. Also, there might be an energy renewable production at the site. And in costs for the purely economic part, it will consist of economic costs and possibly non-monetary costs later on. There still has to be some more research put on that, how to integrate it. And the agent will retrofit the certain option if his utility is higher than a certain threshold. It will be a static variable of an agent. Again, yeah, possibility to gradually sophisticated this decision making and find differences between owner types because they might have different expectations of payback time or different discount rate, and they need to be tuned by the empirical data. So we are planning to do surveys and interviews in the Netherlands, in Amsterdam, as part of the research. And the second, there's another agent, intermediary agent. He will also have his simplified decision making. So in the first step, he informs and makes certain number of building owners aware about retrofitting initiative, and a certain proportion of people will get interested. Then in the next step, the intermediary agent will provide more concrete solutions to those building owners based on this techno-economic submodel. And several buildings will agree to to the retrofitting option. They will become adopters, and we will have number of adopters. And intermediate agents' utilities, of course, also rises based on how many people would adopt, and he becomes maybe more convincing or skillful in the next iteration step. So the simulation narrative is like this. So the model is initialized, agents' buildings are created, then agent states are updated. Then the neighborhoods, if the neighborhood buildings need renovation, then intermediary agent contacts the owners and informs them about the retrofitting initiative. Then if building owner agent is interested, then intermediary agent contacts with customized integrated solution. And then those who are interested might opt for a certain solution, or again, not adopt anything. After that, if it—
5 minutes left, sorry.
Thank you very much. If the retrofitting is implemented, we can see the results, how many people adopted which retrofitting package, and how much energy was saved, how much PV would generate, or other renewables, and of course the costs of renovations. So that is it. And how do we know the results? What other results? We'll have some performance indicators. These are just initial version. So at the end of the this steps will be iterated several times, and then at the end of the simulation time, we will have the number of adopters, and based on that, as I said, to calculate energy and emission savings, annual generation, retrofitting spendings. And what's also interesting, that intermediary agents can also have their costs. So based on how many people they contacted with every step, they will incur also costs, and this will be a proxy for policy costs. If the intermediary agents are like a policy intervention. Apart from that, apart from the introduction of intermediary agents, we can also play with responsibilities of intermediary agents, how he approaches, or his basically how try out different things. And we can do sensitivity analysis with energy prices, CO2 taxes, varying socioeconomic characteristics of homeowners, play with the mix and proportions of agents in the neighborhood, and the buildings as well. Then we can look into maybe housing and rent regulation. If we explore other types of ownerships, we can explore legal framework of condominiums. And this hopefully will give some more insights to policymakers and could be complementary to techno-economic models. Of course, I'm not saying that it will be completely substitute. It will be like a more of a understanding qualitative level model. So there are lots of open questions, and in the future, we of course need to put on some more work on the techno-economic part and identify those retrofitting solutions, and decision-making rules and agent variables and attributes have to be clearly defined, and the scenarios should also be more clearly defined than it is right now. Then I was also plan to start with the implementation of the simple concept to see what is actually possible. And I will use Python, the MESA package for agent-based model. In parallel, we need to collect the data with survey and interviews to define important parameters and validate the model's logic. So yeah, that's it from my side. Thank you for listening, and if you have any questions, I'm happy to answer.
Thank you, Ardak. That was very interesting, and it sounds like it's also fairly complicated. But I'm hoping that your data collection will help you, refine some of the things. Any questions from the audience? Questions.
I have one.
Please go ahead.
Yes, you mentioned that there is some normative statements that you have to monitorize, kind of give it a value, right? To put it in the, to be able to put it in the model. So I think that these, I have the feeling that these points matter a lot, because one often wonders why is there so little retrofitting, and the models would state that there should be more, and therefore, just from an intuitive way, I have the feeling that these non-monetary reasons, they matter a lot. So do you have some idea on how to implement this, put it into the model? So basically, and this then goes into the what if decisions of the agents, right? So like, would you calibrate it in some way, or how do you manage to do it? Do you plan to do it?
Yeah, so basically, there's large body of literature, especially like what affects the building owners in his decision, right? One thing is, for example, it may be his peers or family or their opinions, or his attitude towards generally the energy efficiency or environmental awareness, these kinds of things. They are quite hard to quantify or even define. However, I believe that if we are doing it for a certain case study, for a certain neighborhood, for now the idea is to focus on as for the first case in a neighborhood in Amsterdam, and do the survey there. So if we get kind of the idea what kind of people live there, are they more environmentally aware, and how does that affect their decisions, we could use these surveys or discrete choice experiments to quantify those values, those parameters. I did not put that into it because it gets really complicated for now. I just, trying to keep it simple, implement the first model, and then kind of, while working on a survey itself, already have certain ideas what I want to include. In the case of when the neighborhood is just, let's say, building owners, homeowners, yeah, we can assume that they interact with each other. For example, one person knows two people in the community, and then maybe if one of them does this renovation, the other one kind of gets influenced by it at least a little bit. So this could be one way. But we cannot assume the same in the case of if it's a private landlord or a social housing, because they have different way of thinking there. I would say they're more economical, as they don't get any other benefits like homeowners would care more about comfort, about aesthetics. These are already like proven from the, not proven, but like there's evidence from social scientific research from, yeah, so more or less like that. It's still very raw, but thank you for the question. Hope that answers a bit.
Yes, thanks. So exciting.
Thank you. Any other questions for Ardak? Well, if there's no other questions, then maybe we can move on to the next presentation, who is going to be, I guess, by a colleague of yours from Technische Universität Wien, right? So Ina, that would be your presentation.
Yes.
So please go ahead.
Can you see my screen? So yeah, so good evening, so good afternoon, everybody. I will be presenting this paper, this study today, where I try to identify the relevant parameters to replicate a step-by-step retrofitting optimization model in a building stock level. So as said, Ardak and I, we are PhD candidates in the Technical University of Vienna, and my research focus is the step-by-step retrofitting. Just a quick overview of the content of today. I'll start with an introduction, then go to the research questions, method results, and I'll finalize with conclusions and outlooks. Well, there are some studies and empirical evidences that showed that the step-by-step or partial refurbishment are performed in real buildings. For example, in the study for Germany, the graph shows that there are a lot of high volume on investments for different type of buildings, for example, for the residential buildings, commercial buildings, and public buildings. If we have a closer look on the volume of money invested and for different activities, for the comprehensive refurbishment, partial refurbishment, and repair work, the most volume and money has been invested in the partial refurbishment. Although the policies have until 2018 mainly focused on the single stage, since 2018, the EPPDs, the Energy Performance of Buildings Directive, have recognized the need to have policies that take into consideration the long-term and step-by-step renovation of specific buildings. So the directive introduced the building renovation passports, where it's then regulated. So together with the EPCs, the Energy Performance of Building certificates, the building renovation passport should go deeper and provide more specific recommendations and also specific roadmaps how to increase the energy efficiency and reduce the CO2 emissions of buildings. Going closer on about these roadmaps, there are still not very clear definitions, but it can have different steps. So normally between 2 and 5 steps. If you talk about one step is the single step, and then or not, then if it's the step-by-step approach. And in each step, we have a renovation measure or package of measures. And the idea is then to provide techno-economic specifications of each renovation step, including, for example, the energy savings, the investment costs, and other parameters that are calculated. And the idea is then that this guides the building owners through the renovation process. So the main objective in my PhD and also in my first paper that I have published was to develop a step-by-step retrofitting optimization model to deliver the optimum timing when each step should be performed. I used and tested the model in some roadmaps developed during the IAEE Road project. Just a quick overview, explanation about this IAEE Road project. It was Horizon 2020 founded project where we developed software to provide these roadmaps, these step-by-step renovation roadmaps, and explored this concept and for different building types. So in this, in the context of the project, tested buildings were selected and some energy experts developed these roadmaps, which I'm using it for at 55 buildings. I picked 5 of them and tested my model. There, I did a lot of analysis. I considered, for example, the metrics for assessing the roadmaps. I considered different constraints, but I will not focus today on that. These are already in the paper. I'm focusing today on the outcomes of the method and on the outlook, how I can then use and replicate for the building stock. So the research question for this presentation today is which results were obtained from this first analysis of the model, and based on these learnings, how can deliver plausible budget restrictions for the retrofitting representative for building stock. The reason why I focus also on the budget restrictions is that there are already some reference buildings, as Ardak mentioned, that were specified and suggested by the Tabular project. There are reference buildings that focus on the more on the technical side of the buildings. So there is still a need to create broader approach that considers the budget restrictions, considering other parameters that I will explore here today. So just a quick overview of the method of my model, the main objective function is to maximize the net present value. And we have then the household's cash flow, which is basically the share of income accumulated to spend on energy improvements, energy efficient improvements in the building, minus the investment costs of the energy related investment costs. Here, the important aspect of why is it energy related is because I take into consideration the probability and of the material aging process. So it's a for taking into consideration the aging process of each building element in the building. And over the time, the probability will increase that the material, depending on the lifetime of the material, and this curve of aging process will also determine if it's energy related, so it's a measure that improves the energy, or it's a measure that only it's a maintenance activity. So this also affects the energy, affects the investment costs, minus the energy costs that are basically related to the quality of the building envelope and also the energy carrier in the building, and the operation and maintenance costs that are also related to the energy, to the system, to the technical system. Another aspect that is considered in the model is the budget restriction. that is related also to the share of income, or to the income and the share of income really designated to invest on the energy related costs. Here in this slide, you see the model architecture. So I will start with the input data. There are some, as I said, the roadmaps. There are information related to each step. Then we have the building related data, considering for example, the year of construction, if the building has already went through some renovation and some building elements have been changed. So it's also taken into account. For each building material, or there is a lifetime database behind it, that for the assigned building element, the model reads also the material lifetime. Then there is a technology database that informs the maintenance factor of each heating system. And behind there is also the energy price, and also the energy price development over the optimization period. For this calculation, it was considered optimization period between 2010 and 2050. And with the interest rate of 3%. Well, all this input data is then calculated in a model which was implemented as mixed integer linear programming code that connects to the solver, which was implemented as a Gurobi solver. So the model was implemented in Python, and the outcome of the calculations, they are three mainly. They are the step, the time, the year when each step is performed. From this time, then the net present value of the optimization period, and also the calculated energy savings. What is also important to say is that in a bigger spectrum, the roadmaps can have different steps, as I said, but in this model, we fixed the number of 3 steps, basically because, yes, if we have roadmaps with many number of steps, it might be that the energy savings are achieved very slowly. So it would have to have a plausible number of steps also for the model to calculate each year. So we set this number in 3. Here in this slide, I show you the case studies, the 5 buildings that were selected from the results of the IB Roads project. So it's an overview of the selected buildings. We have buildings in 5 countries, in Portugal, Poland, Bulgaria. They had, of course, different year of constructions, also different net flow areas. The heating system replacement had happened or not, and between the time and the heating system. For all the buildings, I considered a fixed budget restriction of 3,000 euros per year, and did some sensitivities analysis, which I will show you. Then in this slide, you can see how exemplary roadmap can look like. So basically what you have is, so going from left to the right side, you see the ID of this exemplary building is the ID 1. Then the number of steps, 3 steps. So you have the status quo and the description of each measure that was specified, or many measures specified. Then during the project, the energy auditors calculated on the other indicators. Here is just a summary: the primary energy demand after each step, the useful energy, the carbon emission, the investment costs, and the main energy source. Basically, these were also inputs, as I said, to calculate the results. So coming to the results, you see here that we have the first model analysis for the 5 buildings. We have the net present value is the same for all the 5 buildings because, as I said, it was used fixed budget restriction equal for all the building types. Then we have the net present value of the total investments, the energy expenditure, the maintenance expenditure, and the residual value, and the net final. And for the net, yeah, it's interesting because the accumulated asset was maintained constant for all of them. In a comparison, you can see that the net varies in the different buildings, basically because of the technical specifications. So we have buildings there. We have, for example, this building one has less total investment costs, and all these variations depended on the calculated step that was the year of its step that were calculated by the model. So basically, we can see that there are renovations that can have positive net present value, but most of them had also the negative, or the building number 5 was almost 0, I would say. Then in the sensitivity analysis, I had a close look at the budget restrictions and how the model would vary with that. So I calculated a budget of 900 euros, then a budget of 6,000 euros, and the first results were calculated for 3,000 euros. And when we have a look at the results for the different budget restrictions, the model showed a sensitivity to that. For example, for the building 4 that has high investment costs, none of the step 1 or 3 would be performed with lower budget, which means that the building probably will not achieve reasonable energy savings or CO2 reductions. On the other hand, as higher the budget, for higher budgets, you can have a slower process of performing the step. Here, I can also say that it's not infinitive. We cannot say that as higher the budget, as fast the step is performed, because it's also related again to the probability of the aging process of the material. So if the material is not old enough to be replaced, it has then not enough investment costs. Well, seeing that the model is sensitive for the budget restriction, we understood that it's important to have a closer look on the dwelling types and the ownerships. So we did some statistical analysis on the SILK database. The SILK database is it's a database from the European Union that studies households and living conditions of households. And there are a lot of information on the household level. You can see already in this graph here for these different EU countries that the ownership status varies in the countries significantly. We have in blue the single family houses and in green the multi-family houses. For example, what we observe is that the percentage of multi-family houses in Spain is very high in comparison to the Netherlands, for example, where they have high numbers of single-family houses. And it also varies the percentage considering the tenure status. So if it's owner-occupied, if it's the owner paying mortgage, if it's tenant or reduced rented or for free. And here you also see many differences. For example, in Romania, there is a high number, there is a high number, the percentage of single family houses owner-occupied, while in the Netherlands, many of them are paying mortgage. So these kind of differences have to be taken into account when also specifying the types, the building, the reference buildings. Going further,
5 minutes left, sorry.
okay, going further in the analysis, here what you see in this graph, well, the Silk database provides information about the income and the total housing cost. So the idea here was to estimate a proxy indicator for the budget restrictions, but ideally we should use another data sets. We'll explain in the conclusions. So, but here you already see that for the different housing types, there are also very in between countries high differences between, for example, in Sweden, the range between is very high. For example, multifamily housing or with reduced rented is much lower than single family houses where the building owners paying mortgage. And for example, in Bulgaria, this range is less, but in almost all countries, the single family houses paying mortgage, followed by the multifamily houses owner paying mortgage, are the higher, I would say, the higher average of indicator. So yeah, so I'm coming then to the conclusions. To the first research question, I would say that the model provided plausible optimum timing for each step. And the differences on the net and the cash flow, the net present value of the cash flow, was indeed regarding the technical characteristics of the buildings and the energy and the investment costs. In general, we can say that the model calculated a roadmap between 1 and 15 years or 2 and 11 years. These differences were according to the different constraints compared. And as I said, the fixed budget of restrictions of 3,000 euros. More details can see on the paper where this is explanation about the constraints. But one of the main conclusions is that the sensitivities analysis shows that there is a need of being more accurate in terms of the assumptions for the budget restrictions. And when we have to define budget restricted representative for the building stock, well, I think the graph shows that it's interesting to have country-specific budget restrictions that take into account the building type and the tenantry status. We have available for that as I mentioned, the Silk database and the HBS. The HBS database goes on the household budget survey and specifies in many categories all the costs and expenditures that a household has, not the total housing costs that are showed, but it goes deeper. And the ideal approach is then to merge both and try to come with some clusters and possible types. This is this is the step I want to go further, doing some statistical analysis and trying to merge these data sets. So that's it from my side. Thank you.
Thank you very much. That was incredibly interesting. Do we have any questions from the audience?
Yeah, I would have again one. Is it a very interesting approach? Is it possible, because so your analysis is looking forward into the future, but you also have data for the past, right? You have
Yes.
data for buildings when they are constructed and when a retrofitting measure was done. So could you do something like use your model to predict when a building should have done the retrofitting and then see how well it performs comparing to the actual retrofitting that you observed, let's say, over the last 50 years or something?
You mean to compare the past activity with the future one?
No, not with the future one, but to use your model to predict retrofitting, but not in the future, but in the past. So pretend your model works, you know, you're at, let's say, 1960,
Yes.
and you are predicting when the building should have done the retrofitting based on the model, because you have data on the socioeconomic factors from the past and technical, and then you could assess the quality of the model if it accurately predicts the actual fitting that you observed.
Yeah, it's an interesting point. Well, I have done in some previous preparation of the model some deterministic analysis where I tried to, I was in this study, I was trying to understand the renovation cycle based on the material lifetime. So I kind of did that, getting from the constructor year and going through renovation cycles of the materials until now, for example. So I was defining deterministically the past activities, but for this model, I started looking at the future because I am also using predictive energy prices. And but I think this could be also possible to use the model because I can estimate the period. So I set the period between 2020 and 2050, but I could say before and use the data respectively. I think it would be possible, yes.
Mm-hmm.
So may I ask a question of my own, unless somebody else has a more pressing question than me? I don't see any hands up, so maybe I'll go ahead. So I thought that Amir had a great suggestion here. Essentially, it's telling you, your model is essentially telling the consumers, telling homeowners, which one would be the most cost-effective type of interventions, type of retrofitting in the future. But you could also see, if you're using this approach, you could also see whether people seem to have done the most cost-effective type of interventions in the past. And actually, that was, that's related to my question. So, do you have evidence from the data that homeowners are really following some sort of an optimal type of approach over time, whereby they start with the most cost-effective type of approach, type of interventions, and then they do the ones that are less so? Or are they, doing everything at once instead of doing things step by step, or are they doing nothing at all? What do you know from the data?
It's very interesting because this step-by-step approach, one of the most, not criticized, but one of the most, I would say, difficult part is that many people, many specialists believe that doing this step-by-step process, the building owner might not finish the journey. Because, for example, you do the plan, but then, I don't know, the individual, the family situation changes, I don't know, loses the job. So that is the most difficult part in this step-by-step approach, is to make sure that the building owner will finish. And that is also have the data available has showed is that indeed people do not finish. So the most important thing for this is that the policy recommendations and the policy instruments regulates and anticipates this behavior. Like, for example, setting a minimal energy savings per step, or that so to overcome these possible barriers that can avoid that the roadmap is completed, for example. I hope I answered your question.
Very interesting. I like your policy prescriptions, like, you know, the requirement that each step, you know, achieves a certain level of energy, you know, efficiency improvements. Any other questions from the audience? Any questions from the other speakers? I actually took down your the reference from your article because I really would like to take a look at it. I do collect, you know, data on in different places about the renovations that people actually do. And, you know, so one of the questions that I have, you know, from a data set that we're collecting from Ukraine, for example, where the stock of housing is fairly dilapidated, is in fairly poor condition, is whether people do everything at once or whether they spread all of these renovations over time. So I really look forward to reading your article.
Yes, thank you. I'm still trying to look at to evidences, because there is a very, I would say, very detailed study in Germany where they detailed all the renovation activities in the building stock, but it's not such data is not possible for many other countries. So, and the most data that I find is related to single examples. I cannot like go say it's a building stock trend, I would say.
Mm-hmm. Understood. Very good. Well, unless somebody would like to ask additional questions of our speakers or offer suggestions for future research for everyone involved, I would like to thank the speakers for very, very nice presentations and for pioneering something, lines of research that I consider nice blends between economics and engineering, as a matter of fact, so this is really an interesting feature of this particular session. And so I would like to thank you all again, for your wonderful presentations. And I urge everyone in the audience to stay in touch with the speakers, request their papers, request their presentations, which I believe are downloadable at this point. And unless somebody else wants to say something else, maybe we will consider this session concluded for the day. In Europe, it's probably time to get started on the aperitif before dinner. And so I would like to thank you once again and invite you to attend the next sessions of tomorrow of this conference. So thanks again. And thank you also to the session host who has been able to keep track of time very effectively for us. Thanks again.
Yeah, you're welcome. Thank you very much. I would just like to add, thank you to the speakers, and please do not forget to upload your presentations in the dashboard. So if you could do that right now, that would be very helpful. And thank you very much.
Thank you. Bye.
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 Bye.